Okay, so good evening, everybody. So to our statistics video, I think today we'll talk about before we talk about normal distribution and skew data, which I have already introduced in my previous video. I'll just talk briefly on what a dependent and an independent variable is. So I was really trying to get hold of the textbook that I would have loved to recommend to you guys, but I really could not find it anywhere in my files. But just to simply put it, the dependent variable is usually the outcome that we are looking at, the outcome of interest, and then the independent variable is the predictor variable or the explanatory variable. So it is the independent variable that have an effect on the dependent variable. Say you want to find out if the number of hours spent by a student on social media or TV will affect his or her performance. In that instance, the independent variable is the number of hours spent on social media, and then the dependent variable is the performance in the exams. Another example I could quickly give is you want to check if gender, that's male or female, affects certain risk behaviors and certain risk behaviors when it comes to health conditions. That means you're asking, as a male or a female, are they are males subject to having this condition more, or are females subject to having this condition more? So in this case, the independent variable is the gender, that's the male and female, and then the dependent variable is the risk associated with the health behaviors. So if I really come across the textbook that I want to recommend to you guys, I think in my live session I will bring it up. But if I don't, probably you could just look up dependent and independent variables. But what I've said is just simply there is no plenty talks about it. Okay, so back to normal distribution. What is a normal distribution? Normal distribution is a mirror image of itself. It stems from the concept of the central limit theorem. A normal distribution is a parametric data, and there the mean, the median, and the mode, that's the frequencies, are at the zero mark. So the distribution, the normal distribution is also called the Gaussian curve. There is no skewness associated with the normal distribution. There's nothing like right or left skewness. And also I would like to mention that in a normal distribution, that you use the mean and the standard deviation, which helps to give the proper representation. But in a skewed data, which could be right or left, use the median instead. So now I would like to let me see, introduce the concept of standardized normal distribution before I'll talk about the central limit theorem. And please pardon this typographical error. This is supposed to be central and not central. Okay, so there's what we call the standardized normal distribution. And the standardized normal distribution simply just explains, okay, there's in the standardized normal distribution, there's what is called z-score. And the z-score just involves how many standard deviations, just simply means how many standard deviation away from the mean. I think one I would like to draw as I talk. Okay. And this. I think I'll change it to this one. Pardon me if this, okay. So this is the position that so that I could draw pretty well. Okay, so this is plus 1 plus 2 I'm so sorry for the drawings, but I'm just trying my best here. Minus 2. Okay. So what I mean that the normal distribution is a mirror image of itself means that this part here is also equal to this part. They are in equal parts. But there is something called the 68%, the 90, okay, let me confirm that, I'm sorry. 68%, 95%, and 99.7 confidence interval. I mean, let's say 68%, 95%, and the 99.7 rule in a standardized normal distribution. From the name already, before you could use a z-score, you must be sure that your distribution is normally distributed. You cannot use a z-score for a skewed data. Okay, so now from -1, how will I draw this thing now so that it will be easy for us? Okay, so from, yeah, that's -1 to this +1. 68% of the observations are found 1 standard deviation away from the mean. Now, what does this thing mean? -1 means that the score is below the average. This middle, that's the center middle line, is the population mean. So if whatever value you calculate the z-score and it falls within this place, you say that it is 1 standard deviation away, okay, 1 standard deviation below the mean if it is minus, and 1 standard deviation above the mean if it is plus. So it could either be minus or plus, but all in all, you know that it is 1 standard deviation away from the mean. So if it falls within the minus axis, you say that z-score falls 1 standard deviation below the mean. This from here to here is the 68, and note that from -1 to +1, 68% of the observations are 1 standard deviation away from the mean in a normally distributed data. Then from -2, can I change color? Okay, let me use yellow now. So from, no, here is now. Oh no. Will I be able to get this thing I threw before? Yes, I'm so sorry. Let's take it back to blue. Back to blue. Why is this showing eraser? Okay, let's do this again. For some reason, I don't know why it's showing this eraser. Let's come back. All right. Let's go again. Yeah, probably so now we'll draw a larger. Perfect. Yeah. No. Sorry. Let's assume this is our normally distributed data. And normally distributed data, the mean, median, and mode at the center. Here will be plus 1 plus 2 and here will be plus 3. We go here again, minus 1 minus 2 minus 3. Okay, so let's draw. Let's go back to our drawing. And we said from -1 to +1, 68% of our observations fall within 1 standard deviation away from the mean. It could be below or above the population mean. Change color, let's use red. And then from -2 to +2, we say that 95% of observations fall within 2 standard deviation away from the mean, which could be below or above the population mean. Let's use green. And then from -3 to another -3, we say 99.7 of the population, 99.7 of the observation for 3 standard deviations away from the mean, which could be above or below. So now what is the importance of standardizing our normal distribution? Now say for instance, you want to assess, probably you want to assess, you go to a class and you want to assess the not so bright students in the class, or probably the not so bright students in the class are kind of bragging and say, oh, I got to, have you seen Emeka? Emeka got 3. Or okay, I got 5. Let me bring out the example I kind of wrote in my textbook. So I got 5. and then another dull person in the class got 4, another dull person in the class got 3, another dull person in the class got 2, and then the person that got 5 is not bragging, I'm better than you, at least I got 5. The other one is saying, I'm better than you, at least I got 4. Now, what you want to do is that you want to assess if this 1 point difference between 2, 3, 4, and 5. Let me text. 2, 3, 4, 5. These are the marks of the points of the dull persons. Okay, not so bright, pardon me for that word, not so bright persons in class, and they're all bragging to each other. So now you want to, as a statistician, you want to assess if this 1 point differences in their points is actually statistically significant. So what you're going to do is that you're going to standardize this. And we've already made the assumption that this is from a normally distributed data. So what is the formula for z-score? Z-score is equal to the individual x, that's the individual numbers, minus the population mean by x. Can I type by x here? Okay, I don't think I can. Just say the individual x minus the population mean all over the standard deviation. I have to draw. All over text. The standard deviation. So now what we are going to do is that this is supposed to be, sorry, yeah, supposed to be population mean. Eraser. Stop annotating, annotate text is the individual x, that's the individual numbers minus population mean. Text. So z is going to be equal to, okay, so z is equal to the individual numbers minus population mean. So what we are going to do is that we are going to find the population mean. 2 plus 3, 5, 5 plus 5, 10, 10 plus 4 here is going to be equal to 14. And then we'll find the standard deviation. Now, when I did my calculations, the standard deviation was 9.4. So our SD is equal to 9.4. Remember, formula for SD is square root of summation x minus by x all squared divided all over the n as the size of the population. So then to get my z-score, I'm going to do 2 minus 14, which is minus 12, all over 9.4, which is going to give me minus 1.27. I'm so sorry that I cannot do the calculations with 2 here, but probably in a live session, if possible, we'll do it. So I kind of did the calculation already in my book and said I'll just point it out here. So for the first person, let's say the first person is, the z-score is For the first person, the z-score is minus 1.27. For the second person, the z-score is equal to minus 1.17. And then for the third person, the z-score is equal to minus 1.06. For the fourth person, the z-score is equal to minus 0.95. Okay, so it's right, 0. All right, so I think, can I expand this? Okay, 0.95. So now, as you can see, these are the z-scores of the not so bright persons. These are the individual scores scored in their test, 2, 3, 4, 5. But then we calculated the z-score, we got this. Now, if you look at this, you can see that minus 1.27, it falls within this minus 1 to plus 1 range. So it is one standard deviation away from the mean. You can see that the second person is still 1 standard deviation away from the mean. Third, 1 standard deviation away from mean. And fourth, 1 standard deviation away from the mean. Meaning that the 1 point difference in their scores is not statistically significant because all of them still fall within that 1 standard deviation below the mean. So that's basically it. Okay, so what else did I? Okay, so basically that's that for standardized normal distribution. Remember I said the standardized normal distribution is the z-score is only used in normal distribution. Then for the skewed data, let's see if I can undo. Okay, so trying to undo everything. Oh. Okay, so for the skewed data, I'll just draw the diagrams for skewed data. Here, one, and it goes, and then this is going to be, let's use this. This is the right skewed data. And let's go back. Go back. I'm so sorry, these diagrams are awful. But this is, as you can see, wherever the tail of the curve moves, this is the tail of the curve. So this is a left skewed data. This is the tail of the curve. This is a right skewed data. And the skewed data is also known as parametric data. So a recap of what I said, okay, central limit theorem. Let me go to central limit theorem before I do a recap. Okay, so I'm done annotating. Okay, so what is central limit theorem? So the central limit theorem states that the sampling distribution of a sample of the sample means approaches a normal distribution as the sample size gets larger. Study results gotten from the smaller sample size can be used to project to the larger population. So what this is just trying to say is that, okay, I'm going to give a stronger explanation. So central limit theorem, before we talk about it, we have to talk about the fact that before we can carry out okay, how will I start this now? Let's start with sampling. you must have a random sampling, or you must conduct a random sampling to get a sample that actually represents the population mean. So that is what these last two sentences mean. Study results gotten from the sample size can be used to project to the larger population. Now, if you do a convenience sampling, your sample will not be a representation of the population mean. That's your sample mean will not be a representation of the population mean. In statistics, we always assume that our sample mean is a representation of our population mean. Now let's say no, let me annotate this text. This is the let's say the weight. I want to find the average weight. We're just creating a scenario. Please stay with me here. So this is 25 kg. Another one is 34. Another one is 76. Another one is 54. Another one is let's change this to 45. Let's change this to 67. Let's change. Okay, we'll go continue. Another person 79, another person 80, another person, excuse me, 92, another person 82. These are just randomly generated number that I'm given. So another person is 59. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's just make it 10. Another person is 48. So now this central limit theorem. Okay, so let's say we got these values after conducting a random sample, and what's going to happen here is that there's something called sampling with replacements, and that is what is usually done if we want to that is what is usually done in the case of getting probably a value that you can actually project to the public. Let's say you randomly choose out of these numbers 45, 76, 54, you get their means, you put them back. You put the individuals back. Because you sampled them earlier does not mean that you cannot take them again. So that is sampling with replacement means you took them earlier, you put them back into the study, and there is a probability that you take them again. Sampling without replacement is you took them earlier, and because you took them earlier, you cannot take them again. That is sampling without replacement. But in order to kind of get a value that actually projects to the larger population, this central limit theorem encourages us to sample with replacements. We take these values, let's say we take 3, we get their means, then we put these individuals back again. So there's a probability that we can take them again. There's a probability we can take the same individual. But since it's random sampling, you will not know. So when you do this, statistics tells us that when you do this random sampling 30 times, it approaches a normal distribution. And this gets better when your sample size is larger. So that's the way the average blood pressure of 140/90 is. But it's not that everybody it's not that they kind of got the blood pressure of almost everybody. No, what they did is that they did a random sampling to pick up some study participants. After that, they measured their blood pressure and they did sampling with replacement. They did it again, get the means and everything. Now, the mean of the sample means, let's say you sample the first time, sample 1, you get a mean of, let's just say 42 kg. You sample the second time, you get a mean of, let's say 56 kg. You sample the third time, you get a mean of 74 kg. Now, when you plot these several samples on a graph, that's what it means that it approaches a normal distribution. Now, when you get the mean of these sample means, it is the population mean. So that is basically, that is how they got the average blood pressure that we have, or the normal glucose level. It's not as if they took everybody's glucose level. No, they sampled randomly, took the average of the sample by sampling with replacement. They plotted it, and they assumed that since we've done this and we did it more than 30 times, greater than 30 times, it approaches a normal distribution. And then the center line in between, the center line that creates a mirror image in normal distribution, is the population mean. So that is central limit theorem. So I would like to mention that a large standard deviation, like I said, the standard deviation shows the variability, it shows the spread of these values. So a large standard deviation would mean that the values are closer to the mean. What do I mean? Since the spread is large, since the spread is wide enough for, okay, let's say, since the spread is wide enough for a certain variable, the larger the standard deviation, the closer the value falls to the mean. And this is for a standardized normal distribution. And then if your SD is small, means that the variability is not wide enough. That means the distribution is tightly packed. And so even the smallest large value can be identified as an outlier, or a moderately high, adjacent value. So what am I saying in essence? What I'm saying in essence is that if you have a large ST, the value you get is closer to the mean because the variability is wide enough. If you have a small SD, the value you get is further away from the mean because the variability is small and tight. So just to randomly recap, I said z-score is standardized normal distribution, and you use z-score when you really want to know the actual point, like you want to know how significant a point can be. What else did I talk about? I talked about central limit theorem. I talked about the fact that you sample with replacement. Sampling with replacement means that you take the first sample, you get the mean, you replace it back. You take the second sample, you get the mean, you replace them back, meaning that there's a probability that you can take one person over and over again. And if you get a larger sample, it can further be projected to the larger population. What else did I talk about? And that is basically it. Okay, I also talked about one standard deviation, 68% of most observations for one standard deviation away from the mean, 95% two standard deviation away from the mean, and 99.7% for three standard deviations away from the mean. You might not understand this now, but I encourage all of you to keep watching the video over and over and over again. I can tell you that some of the statistics knowledge I have now, I didn't get it from reading once or doing something once. It took constant practice, consistency, and everything. So if you don't get it now, don't be discouraged. Just keep going, keep reading, keep watching the videos, and you will get it. So thank you very much. Next class we'll talk about confidence interval, hypothesis testing, and p-value. To have a nice day ahead.